So back to Lewis structures. I've just got the top right of the periodic table over here, since that's all we need for the non-metals. That's all we'll be referencing. Of course, hydrogen counts, but that's what we want in front of us. So these first three rules you see there in blue, when I did these last week, I kind of put them together like Tinker Toys. The slightly more formal way to do this if you see, the first thing you have to figure out is how are those connected together. That tends to be the hardest part of this, in the sense that everything else that you would do is systematic. But assume just for now that I give you, like what they have there, instead of just giving you the formula, let's say I actually gave you this. And truthfully, I would give you what I call the backbone, where everything has at least one. It isn't that I don't have any like these in the questions, just to show you the formal way. So I call that the backbone. This is not, let me change this. It's not a great example to start with. Let's do CH3CL. All right, so you start with what I call the backbone. It just shows you what's connected to what. This doesn't show you the three-dimensional structure of this molecule. It just shows you what's connected to what. That'll be a little more obvious when we get to molecular shape. But these Lewis structures that we're building literally just show you what's connected to what. It also shows you where the lone pairs are located. But the more formal way to do this is you start by, you need valence electrons, that's an E. You need to count up all the valence electrons that are present for this molecule. We've got one carbon. So do this carbon. We have one of those. Hydrogen. We have three of those. And Cl. I have one of those. So I have one carbon, three hydrogens, and one chlorine. You with me so far? So I've just listed how many are there. How many valence electrons are in carbon? Oh, I've got the part here on the table you need to see. Well, look over there. How many valence electrons in carbon? How many? I've got that. That's a very easy thing to get off the periodic table. Don't miss that. Start with carbon. Count to the left. So 1, 2, 3, 4. 4 valence electrons for a carbon atom. How many for hydrogen? 1. Hydrogen has 1. Chlorine has 7. Good. All right. So to add up all the valence electrons here, there's 4, 3, 7. So add those up. How many is that? Add those up. 14. We're starting with 14 valence electrons, and we've got to work them all into our structure here. First of all, we've already taken up some by these. How many electrons are in this line? Yes, 2. These are the 2 electrons that are being shared between these two. So we've got 2, 4, 6, 8. We've already used 8. I'm going to subtract 8. What is that? 6. So I've got 6 more to put in here. The next thing you do is give every main group element except hydrogen an octet of electrons. All right. Hydrogen never gets an octet.
hydrogen never gets an octet, and boron never gets an octet. And starting with phosphorus and higher can actually have more than 8 around it. So instead of 8, I'll say octet. Maybe I'll say 8 again, but that's what it means. So the hydrogens we're not going to add anything to, because we don't need to get an octet there. Carbon actually has an octet as it is. You count both of the electrons, or whatever it's connected to. So 2, 4, 6, 8, we've already got what we need around carbon. Now we're going to put pairs of electrons on the chlorine. We'll go 2 electrons, 4 electrons, 6 electrons, down to 0, and that's it. That's the formal way of doing this. There are more twists and turns when you get to phosphorus and above. I don't think your book does any of those. There might be one, I'll see. But the trickier part is when there's double bonds and triple bonds. But that's the Lewis structure of this molecule, and that's the formal way to do it. Let's do, see what kind of examples they have. I want one. So just a more wordy way of.
I mean, it wasn't bad to make it. I was just thinking like.
Oh, there's that one.
2 liters or something in the race.
Let's see. Multiple bonds. Let's do.
I wrote in my notes, like in my procedure, I was like 2 liters. And then I was talking to her about it, yes, I made 2 liters. And I was like, what? You did what?
You know, we have this drawn. I want to draw it the same way they did. Let's see. So this is C2, H4. Pretty sure I did this one last Thursday. All right. What am I doing? What am I doing? This. All right, carbon has 4. 2. There's 2 carbons, 4 valence, and then 4 hydrogens, 1 valence each. So we've got 8 plus 4. 2, 4, 6, 8. So we have 12 total valence electrons, and we've already used 2, 4, 6, 8, 10 to get the backbone. So minus 10. I've got 2 left. I have to put a pair somewhere on here. The hydrogens don't get an octet, so I'm leaving those alone. I'm going to put that pair on one of the carbons. It doesn't matter which one. Let me see if that rule actually says. Okay. This says 1, 2, 3. There's actually a 4th step. This one, use multiple bonds to fill octets when needed. So that's a restatement of the rules with more details, but they've added the 4th rule. So I don't do an octet for the hydrogens. I have an octet for carbon. I've got 2, 4, 6, 8. This carbon only has 2, 4, 6. So this is when you make a double bond. We're going to use both of those pairs of electrons to make another line. Now both carbons have an octet. So your cue to start making double bonds is, you've used all your electrons. I should have done that, -2. I'm down to 0, but I still don't have an octet on everything. I was here. I got down to 0 when I put that pair there, but I still didn't have an octet here, so I'm gonna just take that pair and make another bond. And I got a double bond. Let's do. N2. How many valence bonds are in nitrogen? Valence electrons. 5 valence electrons, there's 2 of them, so we have a total of 10 electrons to deal with. Let me go back to the way I did this last week, just as a quick exercise. So to get the Lewis structure of the atom, I would just start counting around 1, 2, no, let me start here, 1, 2, 3, 4, 5. So this is the Lewis structure for nitrogen. Last week I would have told you, you make a pair out of those, then you move those 2 down here, make a pair out of those, you move these 2 down here, make a pair out of those, and that would be the molecule. Triple bond between the 2 nitrogens. You can kind of figure that out without going the formal route, just from making those Lewis structures of atoms and thinking in terms of Tinker Toys and how could you put these things together. The formal way, you would start like this. And I've used 2 electrons there, so -2, I've got 8 left. And now I try to get an octet around everything. So to get an octet around nitrogen, 2, 4, 6. So that's got its octet. 8, now I've used them all. And the problem is this one doesn't have an octet on it. So now we're gonna borrow this pair, and this pair. Now I have an octet. And I can draw these over here, just to be symmetrical. So let me back up. I've got eight electrons left after this 2. I get octet around nitrogen. I start to make an octet around nitrogen over here, but I run out. I've got no more electrons to add. So if I took this pair and made a bond there, that's not going to help me get the octet on nitrogen. That's why I took both of these from over here. So now both nitrogens have any electrons about it. So the more formal way is adding up the electrons and following those 4 rules. Well, I thought they gave me a list of more of those. I will find them here. So I have homework for this, quizzes. But instead of using the quizzes for examples, you have to do all of those. I'm just looking for some to do double and triple bonds.
I'll do some of these. So now I've got, test two, chapter 4 here. Structures. All right. I'll just use whatever's here. Still want. I give up. I'll use these examples. Okay. Something I told you last week, I think I confused some of y'all on this. If you have a formula like those over there, let's do N2H4. N2H4. All right, to add these up. Five valence electrons for each nitrogen. There's 2 of them. H. 1. 4 of them. All right. Hydrogen and all of the halides, fluorine, chlorine, bromine, can all only ever make one bond. If any of the hydrogens in this molecule are connected to each other, then that's all there can be to the molecule. Remember me saying this last week? And then, now there's no room for the other 2 hydrogens or the 2 nitrogens if you do that. So what I'm saying is, when you see hydrogen, you know no hydrogens are connected to each other. So all of those hydrogens have to be connected to nitrogen. Nitrogens. So you kind of have to reason your way sometimes. It also means the nitrogens have to be attached to each other. See what I mean? In nitrogen, that's the Lewis structure for nitrogen. And if we're making a bond there between the 2 nitrogens, now it's obvious where the hydrogens go, right? So the examples where you get a formula, you can reason your way into the backbone by noticing which atoms can only ever make one bond. It's hydrogen and all of the halides. So I will start. I'm going to erase these just so I can do this the formal way. So that's the backbone for this formula. You with me? 14 electrons to put in there. 2, 4, 6, 8, 10. Hydrogens, 2 of those. Yeah, that's right. Okay. We don't put octets around the hydrogens, but we need to get octets around the nitrogens. Put a pair there. X minus 2. I've got 2 left. That has its octet. I put a pair here. Amount of electrons and everything has its octet. That's the Lewis structure for N2H4. You with me? If you follow this procedure, like I said, the trickiest part is when you're given a formula
and you have to figure out the backbone yourself. But once you do that, the rest is just follow along. I wanted more where we have to make double bonds, I can just not find it. Double and triple bonds, I guess I'll have to make some up. What if you had double bond? Did that one last week, but let's do this one again. The formal way. HCN is the formula. Here's the backbone. We've got nitrogen, hydrogen, and carbon. Nitrogen, hydrogen, and carbon. We have one carbon. One nitrogen, one hydrogen, one carbon. 5 valence electrons, 1 valence electron, 4. I'll just add those up. I have 10 total electrons here.
10 valence electrons.
I've used 2 of them to make the backbone. No, I've used 4 of them. 2 there and 2 there, so I have 6 left. I don't need an octet on hydrogen. I've got to get an octet on these 2. It doesn't matter which one I start putting these 2. 2, 4, 6. I'm down to 0. I still need an octet on carbon. I'm going to borrow that pair and that pair, and that's it. Everything has its octet. That's the structure. I'm going to do. What if I took those 6 and went 2, 4, now I've got the octet on carbon, 6, like that. The problem is now I don't have an octet here, so I'd use that pair, use this pair, and it still works out the same. Let's do this. CO. Let's do we've got 2 hydrogens, 1 oxygen, and 1 carbon. 1 carbon, 2 hydrogens, and 1 oxygen. 4 valence electrons for carbon, 1 for hydrogen, and how many for oxygen? Hmm?
6.
So to add them all up, 4, 6. So we've got 12 electrons. Yeah, this is one where you would be given the backbone. So if you were given that as the backbone. So pretend you're starting here instead of being given the formula. 2, 4, 6 in the backbone. We have 6 left. I don't need to mess with the hydrogens. 2 there gives that one an octet. Got 4 left. Do that. So what's the problem I'm left with?
Oxygen doesn't have one.
Oxygen doesn't have the octet.
Carbon has 8 around it, hydrogens don't need 8 around it. This one only has 6 around it, 2, 4, 6. To get more there, I'm gonna steal that pair, and now they all have an octet. Make sense?
There's one more odd thing, but I think I'll save that
Those of you who took a chemistry class before, you remember doing resonance structures? You also remember hating it, right? Other than taking a formula and reasoning out the backbone, all of that's very straightforward. The twists are the resonance structures, when you can actually do it more than one way. And that's when it leads to resonance structures. But let me leave that there. I'm pretty sure, no, I left resonance structures out of this. So this is just a lot of questions that just cover Lewis structures. I put it in here. I guess I didn't put that in there. But that's fine, it goes with resonance structures, okay. So the other thing I want to cover today is called molecular geometry or molecular shape. And I like this website. I'll give a link to this if y'all think you want to play with it. We're stepping into something called, we just say Vesper theory. Valence shell, electron pair repulsion. I know that doesn't really spell Vesper, but that's just what we say. It's an acronym. But here's the theory. If you had, I guess I could do this here. Let's start with just a model, and let's put, all right, so for this, there's a central atom, really the atom that we're focusing on, the purple one. And I've got 3 atoms around it. How many valence electrons are in boron? It's 3. In a case it seems weird that I'm referring to boron when I usually don't, that's because it's a metalloid. But it's a metalloid because it sometimes behaves like a nonmetal and sometimes like a metal. It's in this category where it doesn't get an octet. If it's got 3 valence electrons, that's its Lewis structure as an atom. And if I was doing BH3, I would have the hydrogens here. So that would be a valid Lewis structure. That's perfect. Sketch it. A better representation of it I can actually draw this on the board. This just shows what's connected to what. And when we draw Lewis structures, we tend to do things orthogonal like this, like at right angles. We do your up and down and your side to side. I was doing this with all the other molecules I was drawing. Like when I did that Lewis structure just a few minutes ago. See how I'm doing it straight across and up and down, or just makes this sort of T shape. A better representation of that would really be to do it kind of like this. So it kind of makes this triangle. So I can actually show you the 3-dimensional structure of this. This really is not showing you the 3-dimensional structure.
It's just showing you what's connected to what. And when we do Lewis structures, we tend to do them in this orthogonal way. But since this is a flat molecule, it does actually fit in the plane of the board. That's a slightly better way to draw this. All right, let me show you what I'm getting at with this model. Valence shell electrons, those are just the valence electrons we've been talking about. Repulsion just means they're gonna repel each other. So think of these as being tethered to the central point, and then these white balls out here, the hydrogens in my example up there, or the oxygen and the hydrogens in the other example, are repelling each other to try to get as far away from each other as possible. Maybe you have to think about it for a minute, but that's how they get as far away from each other as possible. Even if they broke the plane, this plane that they're in, they would get closer to each other. Like this one and this one would get closer to each other if they were bent up a little bit. So you have this 180 degrees here. If you made it smaller, all I'm trying to say is, if those are repelling each other and trying to get as far away from each other as possible, that's the shape they're gonna naturally make. That's valence shell electron repulsion theory. The idea that it has this shape because it's really the electrons in the bonds, but there's also electrons around the atoms, but they're repelling each other and they're pushing each other apart. If I took one of these off, I had some molecule that looked like that, that's what they would do. If there's only two things around that central point, they're gonna go straight across. That's how they get as far away from each other as possible. So you can think like this. If there's two things around the central point, if there's three, if there's four, I'm pretty sure your book stops there. If not, I'll go back into it. But so if you have a molecule that has this central point and then two things out here, they're gonna do this. And we call that linear at 180 degrees. I'm not giving you a specific example of that one that's linear, because really I need double bonds there, but I'll come back to that. Do you see why I would say the bond angle is 180 degrees? This is the bond angle, from here around to here. This arc is 180 degrees, and that's obvious, right? If it's linear, it's gonna be 180 degrees. If I stick another one on there, and they're getting as far away from each other as possible, this is groups. When we discuss molecules like this, we call these groups. Another use of the word group. Those of you who took chemistry before, you remember what we call that? Just notice these two things. It kind of makes a triangle, and it's all in one plane. We call that God, are there two N's in that word? Trigonal planar, that's right. So it's a sensible name. This is what we call this molecular shape, trigonal planar. What do you think the angle is? The first one was obvious, it's 180 degrees. This one's actually obvious too, if you think about it. 320. A full circle is 360. You divide that into 3 sections, you get 120. That's a 120 degree bonding. You with me? The one, and I can draw both of these on the board. Linear looks like this. There's a group there, there's the central atom, there's a group there. Trigonal planar, I can actually draw that on the board. This one that's got 4, I can't do that one on the board. Anybody remember what that's called? You took chemistry before. That one's called tetrahedral.
meaning this. Now that there's four things around the central point, it looks like this, and now you can see why I can't really draw that in the plane of the board. You see? It's actually a three-dimensional thing now. You with me? You can have 5 things and you can have 6 things, but I don't believe your book goes into that. You'll probably see that again next semester. Okay, what else do I want to say? Okay, now I have to add something. Oh, this one, the angle's not obvious. It's just kind of something you have to memorize. It's 109.5 degrees. If I drew that in the plane of the board, I would draw it like this. Let's see, do that one straight across. And this one, I don't want to do 90 degrees. I'm going to try to do 109 degrees. Kind of out like that. And then the last two is, this is all in the plane of the board. And then, I'm doing this weird. Suddenly confused. Oh yeah, okay, if I kind of angle it like that, sort of what I have here. Notice that this one's coming towards you, and this one's going back. And this, and this are all together in the plane of the board. So the way we would do that is we do this dash wedge thing. That indicates the one going behind. And the solid wedge indicates the one coming out. So you can kind of draw it in the plane of the board, but you have to use those little graphic tricks. That's more important next semester too, that dash wedge type drawing. All right, 109.5 degrees. All right, now let me back up. Here I've replaced one of the atoms with a pair of electrons. So now I can come up with some better examples. I'm going to move that pair out a little bit and have a little dotted line. So that's showing 4 things, that is 4 groups. Pair. There's 3 things around it and there's 3 atoms. What if there's 3 things around it? Electron pair. That's kind of a null case. And let me just finish this. We've got 4 things around it. If it's all electron pairs, I don't even have a molecule anymore. If I replace, so starting down at the bottom here on the 4, if you've got 4 atoms around it,
like the way I started. We call that tetrahedral bond angle 109.5. I guess I have to stick with what I've done over here. Maybe I can squeeze all this in. Um, That tetrahedral shape, four things around it, all of them are atoms. We say, we would say its molecular shape is tetrahedral 109.5. All right, let me replace one of those atoms with a pair of electrons. It does the same thing. You still get this, basically the same shape, the tetrahedral shape. Bond angle is 109.5, so I would say and this is by groups. All four groups, this is tetrahedral at 109.5. But the actual molecular shape, also known as molecular geometry, I think your book uses the word geometry. What I'm going to put here for molecular shape for this one is you ignore that pair of electrons, you kind of pretend it in there, and you look at what's left. So we're pretending this pair of electrons in there. It is there. But for this idea of molecular shape, we look at just the atoms. What would you be tempted to call that shape if you ignored this pair of electrons? It's got an apex up here, purple. I'll just tell you. Sometimes you can see it. Does it look like a pyramid, maybe? All right. We call that trigonal pyramidal. I always say trigonal pyramidal, but I think it's pronounced pyramidal. It's trigonal because the base of the pyramid is a triangle. The pyramids in Egypt have four corners at the bottom. This has three, so we say trigonal for the base of the pyramid, and the fact that it's shaped like a pyramid. So the molecular shape of a central atom that has four things around it, and one of those things is a pair of electrons, the others are atoms. We say its molecular shape is trigonal pyramidal, and it's still 109.5. So whatever it is by groups, the angle you get, that's what it is when you get molecular shape. Okay. I should be giving you examples of these. So that's an example of trigonal pyramidal. And if I did the Lewis structure of water, that's what I would get. And if I did it in here in my awesome diagram, so it's still tetrahedral, still four things. I'm still going to call it tetrahedral 109.5. Same here. No, I'm not. I'm going to show you that this is like a null case. But by the groups around it, there's still four things around it. So we're still going to say tetrahedral 109.5. But now I'm going to come up with a new name for the molecular shape when I ignore the pairs of electrons. What would you be tempted to call that? It's coming back to anybody. We just call that bent. That's just what we call it. Bent at 109.5 degrees. So
the molecular shape, that is the molecular geometry of water, is bent, bond angle is 109.5 degrees. This last case, if we tried to do that last one where it's 3 pairs of electrons, 3 electron pairs, if we ignore the pairs of electrons, there's really nothing else you can call this but linear. And that's really a null case, can you see that? It's not an open question what the shape will be if there's only 2 atoms connected to each other. It's gonna be a straight line between the 2 of them. It's gonna be, the other straight line I showed you before, there were 3 atoms there. And so there was a question, was this gonna be bent or what? Well, that one was linear at 180 degrees. But when there's only 2 things connected to each other, once we ignore those pairs of electrons, it's always gonna be linear if there's only 2 things. There's the central atom and this atom. So what I'm saying is you don't ever really get asked that question. It's kind of a null case. Of course, it's linear. It's even kind of a null case. So you have this first way you think of it. Has 4 things around it, so it'll be tetrahedral 109.5. The case for that one, there's an example. No pairs of electrons. That was the first thing I had up there. That model would be this. All of them are atoms, so there's no pairs of electrons to ignore. So it just defaults back to tetrahedral with a molecular shape. You with me? So things get shorter here. This is another null case. So let's go back to 3 things around it. And that one I just crossed out. 1 atom and 2 electron pairs. Again, there's only 2 atoms there. There's only one thing to call that linear. You're never going to be asked that question. But what if you had this? So what was this shape? Did I erase it? I did. All in one plane, shaped like a triangle. Trigonal plane. That's this one. And what was the angle? 120 degrees. So that's this first category, but there's no pairs of electrons to ignore, so the molecular shape is okay. It's this case that we get something different. So still three things around it, but one of those things is a pair of electrons. Yeah, okay. So we would say that that's, so I'm here now, 2 atoms in 1 pair. Trigonal planar, 120 degrees. So what do you think we call this? That we just call bent again. But this time it's bent at 120 degrees. Because it's trigonal planar. And the last example. So again, null case. And here we're talking about linear. That's when we had linear, 180 degrees. If one of those is a pair of electrons, then we only have 2 atoms, period, and that's this null case. So the only other one to mention is linear. what if we had that? The example of that one. So now I'm introducing some multiple bonds, got a double bond there. You would get that shape. I'll go ahead and draw it the way you want it drawn. So the groups around this are now, this is one of the groups, this is one of the groups, this is one of the groups. So that one's already on the board. What do you think that is? No pairs of electrons, 3 things around it. I've already written that one on the board. That one's trigonal planar. Again, trigonal planar, 120 degrees. The fact that there's a double bond doesn't really change any of this analysis. These are going to repel each other as much as they can. You're going to get away from each other as much as possible. So that's going to be trigonal planar. What else can I do? I started off showing you a linear one like this. And I guess beryllium does this. It's the one weird exception where you're using a metal. But let me do I should say this. This example, I made you look at it. I made you come up with a trigonal planar. Really, this carbon is trigonal planar. Not this oxygen, not the hydrogens. I was really pointing at this carbon, and that's what I was depicting up there, and saying, what is the molecular shape around that particular atom? The word molecular shape is a little bit of a misnomer. What we mean is the shape of an atom in a molecule. But when it happens to be the central atom for the whole molecule, then yeah, that whole molecule can be described that way. But really, it's the carbon that's trigonal planar. If I don't fill in anything there, you can still see the trigonal planar. So that's worth mentioning. Carbon makes 4 bonds. That molecule, if I did it here, do that. So there's a depiction of that carbon dioxide. And what's its shape? Linear. And the angle? 180 degrees linear. So I have to throw some double bonds in. Now that I clarified that it's a particular atom in the molecule that we're pointing to and giving these words to, let me. All of this analysis is worth seeing and seeing the reasoning behind it, but I like to point out that this is all just about memorizable. So I'll include boron here, just because it shows up just enough. That's where I put it here. Hydrogen can only ever be connected to one other thing. If I'm asking what the molecular shape of hydrogen is in some molecule, that's just a silly question. Again, it's only connected to one other thing. You might be tempted to say linear, but this is why I say these are null cases. This doesn't really have a molecular shape at all. Sure, it's connected to one other atom, but that atom doesn't really have a molecular shape. If you ever ask that, I guess you just say linear. Same with fluorine, chlorine, bromine, iodine. Those will always be, here's fluorine. It's only ever gonna be connected to one other thing as well. So no one's ever really gonna ask you what's the molecular shape around fluorine. You could look at, like, let's say this was that. The molecular shape here really doesn't have any meaning, but maybe this first thing where you just look at groups, you could look at this and say this is tetrahedral because it's got 1, 2, 3, 4 things around it. But no one ever asks you about these either. The ones to know, really the ones that I've approached here, carbon. So carbon, and then here's its Lewis structure. You can have carbon connected to 4 different things. What would it be if it's like this? What's the molecular shape when carbon's like this? The molecular shape of carbon. Tetrahedral, 109.5 degrees. If carbon had a double bond, and then 2 single bonds go into something else, what do you think that is? You wish I had drawn it like this, because I can actually draw that shape on a flat board. But when we're making Lewis structures, we almost always keep it orthogonal. But again, Lewis structures don't show you the 3-dimensional shape. So when you see carbon like this, this was tetrahedral, 109.5. This is trigonal planar, 120 degrees. If you see carbon with it's got a double bond over here and 2 single bonds, it's trigonal planar, 120 degrees. Only other ways you're going to see carbon, it might be triple bonded on this side and a single bond on this side. Vesper theory would tell you that's linear. Because there's no pairs of electrons here, it's just this and this. They repel each other, get as far away apart from each other. And the only other way you'll see carbon, double bond on either side, that's also linear. And it's worth mentioning this because not only carbon, silicon will also do this. Sometimes you'll see some structure with germanium. You rarely see covalent compounds down that far. But anything below carbon, that's it. It's those 4 things to know about carbon and that's it. So you can just about memorize these. And it gets shorter if I go over to nitrogen. So it's really just carbon, nitrogen, oxygen. If you get those, everything else can be inferred because they're the same as you go down the group. Nitrogen, here's the Lewis structure. So you can get nitrogen like that, forming 3 single bonds. That's got 4 things around it. What's its shape? Or what's its shape by group if it's got 4 things around it? Tetrahedral, 109.5 degrees. But we're going to ignore that pair of electrons, and we'll get trigonal pyramidal, still 109.5 degrees. And then you might see nitrogen like this, double bonded to something, single bonded. That's still 3 things around it. I haven't drawn it the way you wish I had because it'd give it away. But I've really kind of got these orthogonal, but what's the shape here? Well, the shape in terms of groups is, same as this, same as this. Trigonal planar, 120 degrees, because I could have drawn it like this. Pair of electrons, single bond. That's really a better depiction of the shape. But when you see nitrogen like that, it's bent. That's nitrogen. Got a double bond going one way, a single bond going another way, and then the pair. And this one was bent at 120 degrees. You see that it's still a triangle? And the only other ways you'll see nitrogen is that null case. I guess you call that linear, but nobody ever asks you about that. So it's those, and then oxygen. You're either gonna see oxygen like that. It's tetrahedral, 109.5 degrees, but you ignore those pairs of electrons. And what's that shape? Bent in 109.5 degrees. And then the last oxygen is null case. No one's ever gonna ask you about that. I guess you could say it's trigonal planar, but then you ignore those pairs of electrons, well, it's gonna be linear no matter what it's connected to. So that's it. If you can memorize those 7, then you don't have to think too deeply about these. But I've given you all the reasoning here.
Is that top nitrogen supposed to be trigonal or tetrahedral?
Trigonal.
Okay.
Yeah, I'm using abbreviations now. This is trigonal planar, this is tetrahedral, this is trigonal pyramidal, this is bent, this is bent. So if you just memorize that much, then you don't have to think too deeply about all of this. Okay. In the 4 minutes I have, let me just show you. Lewis structures and molecular geometry, that's what we just did. I'm gonna open up naming. We went over that last week, but that's just so straightforward, I think you'll remember it. And this is just some questions about covalent bonds. General stuff. We'll do polarity next time. There's stuff to start practicing, so. And if you have questions, bring them in and ask me Thursday, or if you feel lost, schedule some time with me. Where's my sign-in sheet?
Right here.
I just know this because, yeah.